Hi, in this video we're going to look at some antiderivatives that you will need to have memorized. The good thing is that you actually already know some of these. So most of them, there shouldn't actually be much to memorize. Okay, so we're going to kind of just go through and fill out this table, but these are ones you would probably want to put on a flashcard or something and make sure that you know them. All right, so the basic idea here is that the symbols, the integral sign, and the dx are telling us we want to find an antiderivative with respect to x. And for this first one, we just have a constant. So an example would be if we know that the derivative of our function was a constant, like 3. And then we could think about what is the function whose derivative would be 3, right? So if dy dx is 3, then our y as a function of x would be 3x plus maybe some constant, right? So, or if I want the general antiderivative, then all the constants. All right, so our rule here is that whatever that constant is, if I'm finding an antiderivative with respect to x, I will just get that constant times x plus c. So kx plus c. All right, the next one here is for power. And so we did some derivatives on the practice from last time where we looked at functions. Like we looked at a function like y equals 1/7 x to the 7th. And we found that our derivative was x to the 6th. Right? So bring down the exponent, subtract 1. So now we're wanting to go back the other way. So if we know that our derivative is x to the 6th, and then we can think about what our function might be that would have had that derivative. And of course I could have any constant on the end there, right? Okay, so if I kind of look at the pattern between the function that's the power, that's what I have in the integral sign, and the function that is the antiderivative, and pay attention to the exponent and the coefficient out front, then we can write down a little rule here. So out front we're going to have 1 over n plus 1, where n is whatever that power is, and then we'll have x to the power of n plus 1, and then plus c at the end. All right, so that rule works whenever n is not -1. That wouldn't work when n is -1 because we'd have 0 on the bottom of the fraction. All right, the next one though is what would happen if you have x to the -1. X to the -1 is 1 over x. So we want to think about the function whose derivative, dy dx, is 1 over x. And so we did some examples like that last time where we were finding derivatives. We actually had two functions that had the same derivative. So y equals ln of x plus c had a derivative that was 1 over x, but we also had y equals ln of -x plus c, which also had a derivative of 1 over x. So actually, we can think about that. Those two functions have different domains. Ln of x plus c has a domain that is x greater than 0. Ln of -x plus c has a domain that is x less than 0. So if I kind of put those together and think about what that would be when I have a negative value of x and I take the negative of that, that makes it positive. So we can kind of generalize that into one antiderivative form, that the antiderivative of 1 over x is natural log of the absolute value of x plus c. That absolute value is important. A lot of students forget that. Those absolute value bars, those are important though. It's really about the domain. The domain of the function 1 over x is all real numbers except 0. And if I leave off the absolute values on my antiderivative, then I'm leaving off all of those negative values of x. The absolute values make it so that the domain includes negative values of x. All right, this next one should be pretty easy. You know the function whose derivative is e to the x. That's just e to the x is its own derivative. The plus c is the general antiderivative. Notice I have a plus c on the end of all of these. All right, and then we got a bunch of trig ones. So if we think through our trig derivatives, I know the derivative of sine is cosine. So the antiderivative of cosine will be sine. The reason that works is if I differentiate the sine function, I get the cosine function. All right, I know also that the derivative of cosine is negative sine of x. The derivative of cosine is negative sine of x. So if I want to go back the other way and I don't have a minus sign out front, I actually could multiply this equation through by -1 and bring that -1 inside here. We can pull a constant out front. Derivative of negative cosine of x would be negative of negative, so positive sine of x. All right, so if I want the antiderivative of sine of x, I'm going to have negative cosine of x. A lot of students have trouble getting the positives and negatives in the right place for these antiderivatives. So make sure that you work on that some so that you can get those in the right place. All right, you should also know a function whose derivative is secant squared of x. That's tangent of x. Derivative of tangent of x is secant squared of x. So that gives me an antiderivative I know. The derivative of secant x is secant x tangent x. So this antiderivative is also one I just know. If I know a derivative, then I know an antiderivative. All right, I have a couple functions whose derivatives involve cosecants and cotangents. So the derivative of the cotangent function is negative cosecant squared of x. Derivative of cotangent is negative cosecant squared of x. So I can just multiply through by -1 here on this expression, and I'll get that the antiderivative of cosecant squared x, positive cosecant squared x, will be negative cotangent of x. All right, and similarly here, the derivative of cosecant is negative cosecant cotangent. So the antiderivative of positive cosecant cotangent will be negative cosecant of x, and plus c always on the end of all these. All right, we've got a couple more here that should be ones you recognize from earlier in the semester. All right, so the function whose derivative is 1 over x squared plus 1, that is inverse tangent of x plus c. Also, you might remember that the derivative of cotangent inverse of x is negative 1 over x squared plus 1. So if I use a negative out front here, I get an alternate form of that antiderivative. All right, so tangent inverse of x and negative cotangent inverse of x are not the same function, but they differ by a constant. So the plus c on one of these is not exactly the same as the plus c on the other one, but remember c can represent all the possible numbers. So all right, the next one here, the function whose derivative is 1 over square root 1 minus x squared is sine inverse of x plus c, or negative cosine inverse of x plus c. And one more here. So the function whose derivative is this function we have here in this indefinite integral is secant inverse of x plus c, or one way that we sometimes see this last integral written is without the absolute values in the integral, but instead the absolute values in the secant inverse function. So you'll sometimes see it written like this. The integral of 1 over x times the square root of x squared minus 1 without the absolute values is secant inverse of the absolute value of x. And I'm going to have to stick my plus c out here on the end. So it's kind of just a matter of whether you have the absolute values in the original integral or in the result here. So that really kind of has to do with domain of the function and its antiderivative. So, all right, so these are some that you need to memorize. Make sure you put them on a flashcard or on a piece of paper and fold it in half and practice, or keep writing them down over and over again, whatever you use to make sure you have those memorized perfectly. All right, a couple of other things related to what we already did with derivatives before. We know that when I find the derivative of a constant times a function, so if I were going to find the derivative of, say, 5 times sine of x, that 5 would just come along, and then I would have that times the derivative of the sine function. Derivative of sine is cosine. All right, so when I go back the other way, the same deal. That constant, when I go back the other way, is going to just come along out front. So this property says if I have a constant k times a function and I'm wanting to find the antiderivative of, I can just bring that constant out front. That constant comes along, and then times the antiderivative of the function with a big old plus c at the end. All right, one more thing that connects back to derivatives that we did earlier in the semester. I know that if I have a sum of two functions, say tangent of x plus cosine of x, and I want to find the derivative of that sum, I can just differentiate each of those separately. Derivative of tangent is secant squared of x, and derivative of cosine is negative sine of x. All right, so when I go back the other way, the same idea. If I have a sum or a difference of two functions, I can think about that as finding those two antiderivatives separately and then adding or subtracting my results together. Okay, so one important thing to be clear about, though, is that there is no product rule or quotient rule for antiderivatives. And we'll look some at why when we look at some harder problems later, but there is no product or quotient rule for antiderivatives. All right, so yeah, you can't extend that quite backwards the way you can with the sums and the constants with derivatives. Okay, we're going to look at a couple of examples here, and then I'll stop and some more examples in the next video. All right, so we have two examples here of just basic functions that we want to find the antiderivative of. All right, so for this first one, I might notice that I have this constant 7. And I can pull that constant out front. I'm using my property with the constants. It's up here in the table that we just filled in. So I can bring that constant out front of the integral sign. And so this is going to be 7 times the antiderivative of x cubed dx. All right, so I'll have 7 times, and now I'm going to think through my antiderivative rules. So we had one for powers, so that was up near the beginning. I'm going to scroll up really quick to the table here. So the property for powers that we had is the second one that was in my chart here. The integral of x to the n with respect to x is 1 over n plus 1 times x to the n plus 1. All right, so let's go back down to our example and finish that example. All right, so we're going to have 7 times, and then we use that rule. Our n is 3, so when I add 1 to that, I'll have 4, 1/4 x to the 4th. And then I can put a plus c here on the end. So I could clean that up a little bit and make that 7/4 x to the 4th plus c, like that. All right, sometimes I get students that ask a question about, well, shouldn't the 7 be times the whole thing, the whole quantity there? And you can write it like that, but when you distribute through the 7, you'll have 7/4 x to the 4th and then plus 7c, but remember that c represents really all possible constants. So all constants c or all constants times 7 is still all possible constants. So you can just tack that plus c onto the end if you like. This next one illustrates why the differential that's at the end of the integral is important. So this problem is telling us that the differentiation was done with respect to t. So I want a function whose derivative is 4 when I took the derivative with respect to t. So that would tell me that my variable in the problem would have been t. So we'll have 4t, and then we don't want to forget the plus c at the end. 4t plus c. So pay attention to that differential at the end. Particularly on a problem like this, that differential at the end is important. There's no other indication of what the variables in the problem might have been. All right, I'm going to stop the video and then I'll start again and do a few more examples in the next video.